Howdy everyone, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I'm going to explain to you the Bayesian coin example from the book Sivia, 1996, a Bayesian tutorial. Now, so first of all, I'll start out by explaining the problem to you. Then what we're going to do is we're going to look at some interactive Python code using interactive plotting and widgets to be able to make the problem, play with the problem, learn something from the problem, and learn a little Python while doing it. All right. So, what is the problem here? We're going to have a coin. I'm going to pull it out of my pocket. I'm going to show it to you, and you have to make an assessment of, is this a fair coin? So, you want to know what's the probability of that coin having heads? What's the probability of it having tails with every single time that it's flipped? And so we'll focus on heads. Of course, tails is just going to be the opposite, the complement. So we're going to use Bayesian approach to solve this problem. You're going to be able to design a prior model of how you think the coin should perform, which is shown right here. This is the prior. And you're going to be able to use your belief. Maybe you look at me and you say, well, Pyrcz seems like a very honest person, so I anticipate that this is going to be a fair coin. So what you have to do is you got to design a PDF representing the probabilities of different probabilities of heads. Now, if we look at this plot down below, this is a fair coin. That would be 50% probability of heads. If you absolutely believe that I am an honest person, and there's no way I would be walking around with a weighted coin in my pocket, you'd put a spike right there and you'd say, nope, Professor Pyrcz is very honest. It must be a fair coin. Or what could happen is you could say, you know, I really think that Professor Pyrcz is kind of a joker, the type of person who would be, walk around with maybe a two-headed coin in his pocket. And so really you believe that the probability of heads, your prior model, is 100% because that's a two-headed coin. Or you could be in the situation where you think Professor Pyrcz is walking around with a two-tailed coin in his pocket. Probability of heads is 0%. Or maybe you think that I have some type of advanced capability or knowledge around making weighted coins. And in fact, I've created a coin that has some type of distribution where more often than not it will be heads, but with some probability density function. It doesn't, of course, perfectly, it will have some type of weighting. Your most likely estimate is that maybe I have it weighted so that it's about 80% of the time it can be heads, but you're uncertain. You don't know. You just think that I've somehow weighted this coin, but you're not certain about how much it's likely to be heads. You just think it's weighted. Or finally, you might say, I just watch a couple of videos on YouTube. I don't really know this guy personally very well. I don't really know what to think about this coin. I have no information. And so you say, well, it's uniform. I have equal probability across all of from a fair coin all the way to two-tailed coin, to a two-head coin, to something weighted towards heads, to something weighted between tails. They all have equal probability because you really don't have anything to say about the coin. That right there would be a naive prior. Okay, so this is the choice you have to make. You have to formulate a prior model in order to put into this equation. And what's really cool, we can solve this. You'll see when we solve it, we're going to actually bin the problem over a range of different probabilities of heads. And all we have to do is come up with a model that has a description of the density or likelihood for each one of those bins. So as long as we have this at each one of those bins, that's our prior input into this equation, and we can solve this over all of those bins. Now what I'll do next is I'll talk about the likelihood model. All right, now let's talk about the likelihood. So the likelihood is this part of the equation right here. It's the probability of the outcome from the experiment given the coin. So likelihood function right here. Okay, so how's it look? So we already got the prior model and you drew a function. You said Pyrcz is honest. It's going to be I'm certainly going to be a 50-50 coin, or I don't know Pyrcz, complete naive, or weighted one way or the other with some uncertainty. You decide it. Now what you're going to do is you're going to take that coin from me and you're going to run an experiment. And you're going to keep tossing the coin. Every time you toss the coin, you're going to get heads or tails. Tails, heads, 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 tails, and so forth. You can just keep going. And you'll keep tossing the coin, and you'll get a certain number of possible outcomes. You'll have a number of heads and a number of tails. And if you take both of them, add them together, that's going to get you the total number of trials. Now, what you need to do is for all of the possible, remember, we discretized the probability of heads, where that would be 50% right there, and maybe 55 or 60 or 70 or 80, all the way up to 100% right here. We need to calculate for each one of those probability of heads in the coin. Now we got to calculate the probability of the experiment, the tosses given that coin. And the great thing is we have the binomial distribution. The binomial distribution equation is shown right here. It provides a PDF, probability density function, for the following: the total number of trials, total number of successes, which we will call heads, the probability of heads to the power of number of heads. Well, guess what? For this case here, it might have been 5% or 6% or something. We go ahead and put that for P. And we look at our experiment. We got a number of heads, number of tails. We can put that in. Number of heads is the X. Number of total experiments is going to be number of heads plus number of tails. And we can go ahead and take 1 minus this probability and to the power of the number of trials minus the number of successes. This is the probability of the failures. And of course, this is the choose operator, n choose x. So basically, what is this? It's assuming independent success failure binary outcomes with a probability of the success of P. You have this many successes, so independence, just probability of success times the probability of success times the probability of success gives you the probability of that combination. 1 minus, this is the probability of failure, total number of failures. So this is assuming independence of all the probabilities, and this choose operator is accounting for the combination of ways it can happen. Because we could have heads, tails, 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 heads, tails, or tails, tails, heads would all be cases of 2 tails, 1 heads for 3 tosses. But we have 3 combinations to get there, and so the choose operator accounts for that. All right, so we get the binomial representation here, so we can just plug and chug. All we have to do is supply into this number of heads is X, number of successes. The number of heads plus number of tails is going to be the big N. And so we're able to calculate. And what we'll find is if we had an experiment that was 50-50, what we're going to find, heads and tails, is we'll have a distribution that's nicely shaped, and it'll come back down, and the mode will be right at the 50%. Now, if we run fewer experiments, what'll happen is the distribution won't be as steep. It'll have more variance because you have more uncertainty. And if we ran many, many, many experiments and it's 50-50, the uncertainty would go down. So that's the binomial distribution that we're working with. Now, if we were closer to the edges, it can, of course, become skewed. So don't mix it up and think that's a Gaussian distribution. But if you're right on the edge, it'll become skewed and have that shape. So that's how we're going to calculate the likelihood. Now, what's really cool is once we have the likelihood for all of these probability of heads for the coins, we can take the prior times the likelihood, and we're able to go ahead and solve for the posterior. Now, I should make a couple of comments about the evidence term. The evidence term is really just going to be a standardization of forced closure. What we can do is just solve this for all of our bins and then divide it by the total sum over the bins. That will force the area under the curve, or the summation across all these probabilities, to sum to 1. That's closure. That's exactly what the evidence term would be doing for us. So we'll just do closure at the end through a standardization, dividing all of the probabilities by the sum of the probabilities to force the posterior distribution to sum to 1. All right, so that's exactly how we're going to get this done. Let's switch to the code and take a look at the code. So here's the Python code. It's in a Jupyter notebook, and we're going to be able to accomplish this approach of Bayesian updating to figure out if a coin is fair based on a prior model and a likelihood model coming from the binomial distribution and a set of coin tosses, and to get to a posterior distribution, and we're going to do it all interactively. Okay, so this is what it looks like. Every time I do one of these examples in Jupyter Notebooks, I like to put a little bit of some links, introduction, explain the experiment. So this is all explained right here, kind of short and to the point. We're going to go ahead. We want to work with some parametric distributions. I ended up working the binomial and the Gaussian distribution. I tried experimenting with the triangular for a prior. That was kind of cool. I ended up going towards a normal distribution. I thought that was better control of the experiment. But of course, anything could be done. You could even try to hand draw or edit in the values if you like. Let's go ahead and import those packages to work with. We're going to also need IPy widgets, and we can import interactive, and that's how we'll get our interactive plotting going. And we're just going to work with matplotlib. I like doing things really simple. We'll need NumPy to do some array math, broadcast methods that are nice and quick, and we should be good to go. Now here's the code. Really, really straightforward. What I need to do is I'm going to declare 4 widgets to work with. Now each one of the widgets are going to describe different parts of the inputs for the experiment. The first widget is simply going to be the coin bias. That's my prior model, and that dial will go between 0 and 1, and that's where I think the mode or the most likely value is for the coin. If I think the coin is fair, I'll put on 50% heads. If I think it's biased one way, like more often getting heads, I'll go above 50%, and so forth. Now then I also want to put in a coin uncertainty term. I'm using a Gaussian distribution for the prior, and so you can change the dispersion. Maybe you say it's 50% with high certainty, low variance, and that's exactly what that is. And then you'll be like, hey, Pyrcz is honest. I know this coin's going to be good. It's going to be fine. Or maybe you're going to go ahead and say, you know what, I don't know Pyrcz very well. A naive prior, in the case of Gaussian distribution, is a very wide dispersion relative to the problem, and that will result in the prior actually having no control in the problem, and we'll see that. Okay, and then the other widgets we want to work with, our B widget is going to be the B and the C are going to be the outcome of our experiment. And I thought a nice way to do it would be over the experiment, what was the proportion of heads observed? So this is a proportion. It's easier that way than having separate heads and tails dials. I thought that was clean. And then the C dial or slider is an integer slider, which is the total number of coin tosses. Now what we're going to observe is as we shift to a higher proportion of heads, the likelihood term will shift to be more the probability of the tosses given the coin will indicate a higher probability with regard to these higher bias terms within the coin. And as we increase the number of tosses in total, the uncertainty is going to shrink. So we're going to get to see all of that. That's really cool, the interactions between everything. So we have defined a function here. It's going to read in the information from the slider, A, B, C, and D. A and B are prior information, the mode or mean of the bias, the variance of the bias, the prior. And C is going to be the total proportion of heads in the experiment. D is the total number of trials or coin tosses. Okay, so we're in pretty good shape now. I like to use regular, simple, easy to interpret code. So I'll say, okay, just tell me the number of heads, number of tails from that experiment. And so both of those should be integers. Then what I want to do, I want to discretize the probability of heads from 0 to 1, 1,000 times, so I get nice clean functions to look at. They're really nice and clean. I'm going to define the prior. The prior is really simple. I gave the mean, I gave the scale parameter, the measure of dispersion as d, and I force closure on the function. I force the sum of all of the bins to be equal to 100%. I just like to do that. It's very clean for me. If I looked at the probabilities on a table, they would be valid probability values. And I like that. Okay, so now we're going to go ahead and define a plot with the prior distribution. We'll just plot the prior distribution. We're going to have a 2x2 matrix plot in this function. Now you notice this is a little bit inefficient because every time you touch a slider, it's going to reproduce all of the plots. I didn't do anything fancy with trying to only update certain plots. Remember, I just kept this very simple. There'll be a little bit of flicker in it. It shouldn't be too bad. It's not that heavy computationally. Okay, so we'll set the limits on the x, 0 through 1. The x-axis is going to be the probability of heads from my prior model. And we'll put labels on the plot. We'll plot it up. The second plot is going to simply be a pie chart. And now I got a little fancy with the pie chart. I'm kind of proud. What it's going to do is you enter the total number of trials or number of tosses and proportion of heads. It's going to just show you proportion of heads, proportion of tails, and the size of the pie chart will increase as you do more trials. It's kind of fun. Okay, so we go ahead and we have that, but we also want to create the binomial distribution. Well, isn't that great? In SciPy, we actually have the binomial distribution already coded up for us. We can get the probability density function discretized, and so all we have to do is tell it how many successes did we have, how many total trials did we have, and what was the probability of heads that we're assuming for the coin. And we do that for all those bins. There's 1,000 bins from 0 to 1, 100% chance of tails to 100% chance of heads and everything in between. And we'll get the binomial distribution and we can look at that. That's our likelihood function. It's going to be our likelihood function. It'll be really useful so we can see how the experiment is providing new information. Then once we have that likelihood, the final thing we can do is we'll just take that. It's a one-dimensional array of the probabilities discretized across the completely tail-weighted coin, double tails, all the way to double heads and everything in between. We can just apply Bayesian updating, the prior multiplied by the likelihood. Now I mentioned I haven't calculated the evidence term. The evidence term is just there for closure. So all I have to do is take that one-dimensional array of posterior values right here, calculate its sum, and divide it by itself. That's closure. It's going to force closure so that all of these probabilities sum to 100%. And so that works. And then we can plot the posterior. Now, in order to get this to come alive, to start being interactive, all we have to do is call this widgets.interactiveOutput. We refer to the function that does our plotting, and we just tell it to link up and use all of the A, B, C, D up above here we defined as widgets, float sliders, and then an integer slider for the total number of experiments. Okay, so that'll make it come alive. Now I put this command here, clear output, wait equals true, because I was having some flickering problems, and you'll see what it does. It makes it just sit there, and it doesn't immediately update. And I think that's useful because it seemed to me that it was trying to update every time I moved a little bit. It was updating and replotting the charts, and it just made it a bit laggy. So this has improved the performance. All right, so now what we'll do is, well, I just realized, I just realized that I'd forgotten to import widgets. And so when I ran it, I got an error. So just to take you back up here and mention, we need to import interactive and also widgets. Interactive will do the connectivity of the widget to the function for the plotting, and the widgets will allow us to have the access to the sliders and all. So we can go ahead and run this code right here. And now we have our function. We have our widgets, we have our function. What's missing now? We need to display it. When we run this code right here, and I already ran it just now, but if we run it, look at this, we got our widgets. Now, I didn't mention it, but we did use an H box in order to organize our widgets. And if you look back at the code, you'll see I actually did take the widgets, define all the widgets, and then create an horizontal box of widgets with all of them listed. You can do so much to build like a full UI, user interface, with all kinds of how does it scale when you move it, when you shrink it, how does it format. I actually spent a little bit of time as doing full stack development in C++ and worked with Qt for a while, and it's kind of getting like that, where you can kind of control everything really nicely with the display. Okay, so now what'll happen, let's go ahead and just change the coin bias. Okay, so let's take a look at what we've actually done. So as soon as you move one of the dials, it comes alive because I put that wait command in there. Not a big deal. Okay, so let's go ahead and make some changes. The first thing is we said 50-50 proportion of heads observed in the experiment, and we did 100 coin tosses. So that's literally 50 coin tosses head, 50 coin tosses tails. Let's go ahead, if we look at the likelihood term right here, and we go ahead and increase the number of coin tosses. Look at what happens. Isn't that cool? And you see this plot grows. Now we have 610 coin tosses. Do you see what's happening? This distribution is becoming narrower. We're conserving the area under the curve, and it's becoming narrower and narrower because of more coin tosses. We're much more certain with regard to the actual experimental outcome and what it's telling us about the bias in the coin. Okay, we got more and more information. Now look what happens if I change the proportion of heads observed in the experiment. Now you see how that distribution shifted to 30%. We could even take it all the way down to 10%. You see what happened? If I take it up to 90% or 80%, 90% heads right there, now the likelihood function is changing significantly. You're getting a lot of good information. Okay, so let's go ahead. Let's shift the total number of coin tosses small again. So you see how it's shrinking, a little bit of flickering, but not too bad. Let's go ahead and take it to something really small. Okay, so proportion heads, 50%, and we had only 5 coin tosses. Now what's going on? You can't have half coin heads when you only have 5 coin tosses. Let's go ahead. Yeah, good. 6 coin tosses, 50-50, 3 heads, 3 tails. Look at this. A very broad likelihood. It's getting quite naive. You have very little information. Now let's go back and look at the prior distribution. Let's say that you decide that I'm a fair person. So you put the 50% is what you think is the most likely value for the coin. You think it's most likely a fair coin, and you think it has very low uncertainty. In other words, you put a spike on 50%, said purchase fair. If I think the coin could have a little bit of dust or dirt on it, that might actually change the heads, probability of heads, maybe just a little bit around 50%, 50-50, but it should be fair. Now look what happens. You have a naive likelihood. You threw the coin very few times, and you have a very specific prior, and look what happened. The posterior is basically just mirroring the prior. You didn't have any, really not too much new information. Okay, so now let's go ahead and say that you increase the amount of information in the likelihood. You did quite a few coin tosses. Now this is going to grow. Look what happens. You see how this is growing right here? You had a prior that said purchase fair, his coin is fair. You had a likelihood that's showing the same thing, and you ran a lot of experiments showing the same thing, and now your posterior is even more certain that my coin is fair. In fact, if you keep running the experiment, look at what happens. You see that? Isn't that great? Look at that. This is providing a lot of information, and the posterior is saying, yep, this coin certainly is fair. Now, we can do some other things. Let's go ahead and say, well, what if you run the experiment? You thought the coin is fair, you run the experiment, but then something goes weird. It looks like as if the coin is weighted towards 70% probability of heads. And so you ran quite a few experiments. It's actually pretty narrow on that. Now look at what's happened. Your prior was purchase fair. Your likelihood is taking you towards a bias towards heads, and your posterior is going to be a compromise between the two. Its mode looks like it's somewhere around 0.55, 0.57, but the experiment was saying a mode most likely the coin is somewhere around 0.7. Yeah, which is right here, 0.7, 70% chance of heads. But your prior was 50-50, and so you're somewhere in the middle. Okay, so we can see all kinds of interesting things happening right here. Let's go back to your prior, And let's say that you were really uncertain. You didn't really have much information. Pyrcz, I don't know. I watched some of his lectures. I'm not sure if he's got, cheating with a coin. He's got double head, double tails. You see how this is very uniform. It's a uniform distribution. We put a huge variance or dispersion on it. Look at what happens here. The likelihood term becomes the same as the posterior. The prior provides no information. Okay, I think this is so much fun. This was an example of using great Python packages like Widgets for interactivity with Matplotlib. Not very fancy, not very difficult. Actually, if you look at it, we were just able to define some sliders, put them in an H box, define a function that created the plots, and just tell it to link them up. Take the sliders, use it to populate the values into my function, and just told it to go ahead and create those plots. And we now have this nice interactive GUI that we can play with and understand the coin example from the book Sivia, 1996. All right, so I hope this was helpful to you. I'm Michael Pyrcz. I'm a professor at University of Texas at Austin, and I teach and conduct research in data analytics, machine learning, and geostatistics. We have some exciting new papers that just came out, brand new novel ways to model the velocity fields in intergranular scale, the pore structures of rock. And I have a new paper that just came out with modern ways to use machine learning for building subsurface models using deep convolutional generative adversarial networks, and even some really interesting spatial data analytics to methodologies to drive decision-making in subsurface development. That came out just in December. Anyway, I'm always happy to discuss. Hey, take care, everyone.